Hey folks, in this video we're going to talk about the acceleration of gravity. So first we have the equation for the force of gravity, Newton's universal law of gravity, which is this one here. Okay, and so how do we make this into an acceleration? Okay, well, we have another equation for the force of gravity, aka weight. Okay, and you already know this one. You've been using it for a while. Force of gravity equals mg. Well, these are measuring the same thing. Now, let's say this is the Earth and you. Okay, so let's say mass 1 is the Earth and mass 2 is you. Which one's going to go in here? Well, that's going to be the mass of you, okay? Because you want to know what the force on you is, okay? So we're going to set these two equations equal. So negative g, mass of the Earth, mass of you over radius squared equals mass of you times g. Oh, and then we're just going to look at magnitude, so don't worry about that negative sign there. All right, well, you'll hopefully notice that your mass drops out and you get an equation for little g. So this is the acceleration caused by the force of gravity. And little g is, now there's actually negative, and I'll explain that in a second. Big G, mass of whatever is causing the acceleration divided by r squared. Now, again, a reminder, oh, and that should be in the r hat direction, meaning radially inward. Now, as a reminder, radius, okay, so that's the distance from the center of one object to the center of the other. So if you're talking about you standing on the surface of the Earth, you would plug in the radius of the Earth, technically plus about a meter from the ground to you, but that 1 meter ain't going to matter because the radius of the Earth is like 6 million meters, so 1 more meter ain't going to matter. So basically, in this case, you'd plug in the radius of the Earth, okay? Now, if you were to plug in the radius of the Earth, the mass of the Earth, and big G, which is 6.67 e negative 11, you're going to get about 9.8 within rounding, okay? Because that's what the acceleration of gravity here is at the surface of the Earth. Now, by the way, the one other thing I'll mention is this is actually called a field, okay? That acceleration of gravity, it's all around the Earth, okay? And we'll talk more about field theory when we talk about second semester in electricity and electric fields and magnetic fields. But for now, the way you can think of this is, I guess one way to think of this is that the Earth affects the space around it. And this is a measure of how affected that space is, okay? And if you put something in that space, it will move or it will feel a force, okay, because of the Earth affecting that space. So we'll get off of that for now. Let's try some examples. Okay, so again, if you were to plug in big G, mass of the Earth, and radius of the Earth in here, you're going to get about 9.8. What if you climb up to the top of Mount Everest? So let's say here's Mount Everest, and then you climb to the top of that, okay? Well, Mount Everest is about 8,848 meters from the surface of the Earth to the tip of Mount Everest. I looked that up. So what would little g be up there? Like, would you feel lighter up there? Okay, so let's try that out. So little g at the top of Mount Everest would be, okay, so we got 6.67 times 10 to the negative 11th. The mass of the Earth is approximately 5.97 times 10 to the 24th kilograms over, now here's where you have to do some work here. You have to take the radius of the Earth, which is 6.38 times 10 to the 6 meters, plus the height of Mount Everest above the Earth's surface, which is approximately, again, 8,848 meters. And then we square that. If you plug all that into your calculator, you get about 9.76 meters per second per second. So would you feel lighter at the top of Mount Everest? Technically, you feel a teeny bit lighter, you know, about 0.5% lighter or so. Actually, more like 1/3% lighter or so. But would you notice it? Nah, you'd probably be too tired to notice the difference, okay? Now, on the other hand, what if you are in the International Space Station? So here's the Earth, and here's the International Space Station. Now, the International Space Station orbits at a height of approximately 211 miles on average above the Earth's surface. Okay, what's little g up there? Okay, so you would do the exact same calculation. The only difference is this number here, this height. Now remember, you got to use meters. So this height would be 211 times there is 1609 meters per mile. So that's what would go in instead of your 8,848. But all the rest of the numbers would be the same. If you do this calculation, so this is the value of little g at the location of the International Space Station. Now, let me make this really clear. This is not little g caused by the space station. This is little g of the Earth at the location of the International Space Station. And if you do all the math and plug your numbers in, you get about 8.82 meters per second per second. Now, hold on your horses here. Okay, is that less than 9.8 at the surface of the Earth? Yes. Is it a lot less? No, it's about 10% less, okay? Which means if you're an astronaut in an International Space Station, for instance, me, I'll use me as an example. On the Earth here, I weigh about 180 pounds. Up there, I'd weigh about 160 pounds. Well, hold on a minute. How come they don't feel their weight? Okay, aren't they supposed to be weightless? Aren't they supposed to be floating around? Well, no, they're not weightless. Matter of fact, if they were weightless, we'd be in trouble. Let's say they were orbiting this direction. Well, Newton's first law says they want to go straight. Well, something has to bend them in a circle. Otherwise, they're going to go in a straight line and never, ever come back. Well, their weight is what bends them, thankfully, in the circle. We'll talk about that shortly with orbit, okay? But for this example, here's what's happening. Imagine I were to put you in a big, giant room, lift you up really high, and then drop you. As we accelerated toward the ground, you would feel weightless. Does that mean you're weightless? No, your weight is what's pulling you toward the ground, right? But you wouldn't feel your weight. Well, we never feel our weight. The force that we feel is the normal force. So right now, odds are you're probably sitting in a chair. You don't feel your weight. What you feel is the chair pushing up on your rear end. That's the normal force. You might also feel the ground pushing up on your feet. That's part of the normal force, okay? Well, when we drop our room, you are normal forceless. The normal force is no longer acting on you. So you perceive that to be weightless. It doesn't mean you're weightless. It just means you're normal forceless. It's just like when you dive off a diving board. While you're in the air, you may feel weightless, but you ain't. But you are normal forceless, okay? So if you were to take the International Space Station and just flat out stop it and hold it there in place, their astronauts would all, boom, they'd hit the ground. They'd all feel pretty normal. They'd feel about 10% lighter than normal. So like, for instance, me, instead of weighing 180 pounds, I'd weigh about 160 pounds up there. But otherwise, we'd all feel pretty much at normal. The reason we don't, an astronaut doesn't when they're orbiting, is because they're orbiting and they're, in essence, falling around the Earth, which we'll talk about shortly, okay? Now, there's one more example I want to do with little g. It's kind of fun. And that is, what if you're on an asteroid? Okay, so this is an asteroid. It's a rather large one. Here's the International Space Station. There's a picture what it would look like next to it. So it gives you a frame of reference. It's a pretty big beam there. And we've got some data. We've got the length of the beam. And down here, I looked up the mass of this thing. And you could find it there if you wanted to know some data about it. So let's say we were standing right here where this rock is. What would little g be there? Okay, right there. Now notice that's about half of this distance, so about 270 meters from the center of the asteroid. So that's what we're going to use for our radius. So let's say you're standing right there. What's little g? Well, here's the mass that I'm going to use right there. And the radius I'm going to use 270. So we'll say little g of the asteroid in this asteroid happens to be big G, which I'm not going to write out, but it's 6.67 e to the negative 11th, times the mass of the asteroid, which we just saw was 3.58 times 10 to the 10th kilograms. So it's a lot less than the Earth, right? Over radius, which is 270 squared. And if you plug and chug, you get about 3.28 times 10 to the negative 5th meters per second, okay? Now, to give you an idea what that means, okay, Well, first of all, that's incredibly tiny. The gravity on this thing is incredibly tiny. Just to give you an example, the force of gravity on me, now remember my mass is approximately 80 kilograms, would be 80 times this number, which would be 0.0026 newtons, okay, which would be some very small fraction of an ounce. So while we're not weightless on this asteroid, we are awfully darn close, okay? Now, later on, we will talk about how to orbit the asteroid and how fast you'd have to jump so that you'd never come back. Okay, that's for a future video. So I hope you enjoyed the video, and thank you very much.